Hi everyone, I'm Sujani, Faculty in Physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about Zener Diode. We have been seeing a series of lectures on semiconductor devices. We have already done with direct and indirect gaps, PN junction and voltage current characteristics, the energy band diagram and the biasing of a junction. So today we'll be discussing about Zener Diode, and let us look at the brief outline of this topic. First we'll see the introduction for Zener Diode and what is the symbol we are going to use for a Zener Diode whenever we put it in a circuit. And then the construction of a Zener Diode, how a Zener Diode is made and the working of a Zener Diode. And then we will discuss the voltage current characteristics of the Zener Diode in forward as well as reverse. And also we will see the applications of Zener Diode. So coming to the definition of what a Zener Diode is. It is a special type of PN junction diode that operates in reverse bias, and more specifically in the breakdown region. So these 3 points are very important. A Zener diode is nothing but a PN junction diode, but it is specially designed to operate in the breakdown region in reverse bias mode. And how this Zener diode is different from a PN junction diode is the doping level of the Zener diode is somewhat higher than that in a PN junction diode. So to understand PN junction diode, we will also see very briefly the PN junction and its working, so that we can easily understand how a Zener diode is made and how it works. Coming to the symbol is somewhat similar to that of a PN junction diode. If you see a PN junction diode, this is the symbol for a normal PN junction diode, a triangle with a line. This is the positive, or we say it is connected to the anode, and this is negative, we call it is connected to the cathode. This is for a normal PN junction diode. Now what is the symbol for a Zener diode? This line, there is a small bend at both the ends. So you see these are the bends. In addition to this, there are bends. So this is the symbol for a Zener diode. I say this is positive, negative, or this is connected to the anode and this is connected to the cathode. So in Zener diode, we have an N-type semiconducting material and a P-type substrate that are diffused together. We have seen different methods of formation of PN junction. So here we are using the diffusion technique. So if you see in the diagram here, you take an N-type material and diffuse it into the P-type substrate. That is how a PN junction is formed. So first we are talking about the PN junction, and then we will see how we are making it different for a Zener diode. And now we are going to cover the junction region with a layer of silicon dioxide. So you can see here, this is the layer of silicon dioxide. So the junction layer is always covered with silicon dioxide. This helps in prevention of the contamination of the junctions. That is why we do this covering with silicon dioxide. And also the whole assembly is metallized, means we'll have metal contacts on both the sides. So this is the metallic layer here. The green one you can see here, this is the metallic layer, and on the bottom also we have a metallic layer. So this helps us to have the connections, electrical contacts to generate anode and cathode connection. So this is the metallic layer which may be connected to the cathode, and this is the metallic layer here which is connected to the anode. So what we have in PN junction diode here is an N-type material is diffused into the P-type substrate, and then at the junction we have a layer of silicon dioxide which is used to prevent the contamination, and then on both the sides we have these metallic layers which help us to have the contacts, electrical contacts connected to the cathode and the anode. Now when it comes to working, first we'll understand the working of a PN junction, and then we will see the working of a Zener diode. Then things become very clear. So when P and N-type materials are joined, in the region of contact, the electrons diffuse from N region and combine with the holes in the P region. So now we take a normal PN junction diode. So this is the PN junction we are taking. So this is the P region and this is the N region. When they are brought together, the atoms of the P side will combine with the atoms of the N side, and then we will have this junction, and this junction we are calling it as PN junction. And now we know that in the P region, holes are the majority carriers, and in the N region, electrons are the majority carriers. Now when holes are majority here and electrons are majority here, because of diffusion, diffusion means the process of movement of charge carriers from higher concentration to lower concentration. So the concentration of holes is more here. The holes will try to diffuse into the N-type, and here electrons are more on the N side. So the electrons will try to diffuse onto the P side. So thus there is movement of electrons and holes across the junction. Now when these electrons and holes move, first we see the electrons, they lose their energy and become immobile negative ions. So what is happening here when the holes are coming? Here they are losing their energy and they will become immobile negative ions. Similarly, when the holes are diffusing from the P region and combining with electrons in the N region, they lose their energy and they become positive immobile ions. So what we have near the junction is positive immobile ions on the N side and negative immobile ions on the P side. There are layers that are formed on either side of the junction. Now what happens? This leaves the N region near the boundary positively charged and the P region negatively charged. So you see here, this is negatively charged. All this is negatively charged towards the P region, and this is positively charged towards the N region, because of which there is an electric field EB that is developed. So we can see the electric field that is developed. So I can denote it by this. This denotes that there is an electric field that is developed across the junction. Now this region will be depleted of charges because the electric field will remove all the charges that are present inside. They will sweep away all the charges, and there is a region that is formed which is depleted of all the charges, and we call it as depletion region. This region we call it as depletion region. The thickness of this depletion region is very small, of the order of 6 into 10 power minus 6 centimeter. And what happens here is there is a potential difference that is generated across the junction, and we call it as contact potential or barrier potential. Means there is a barrier that is formed for the further movement of electrons and holes from P side onto the N side or N side to the P side. So the movement is stopped. Now what we have to do is to do biasing. What is biasing? It is an arrangement made in the diode or any electrical device to allow a larger flow of current. So when the movement of these charge carriers is stopped, there is no current. But by biasing, what we do is we will lower the potential barrier, thereby making or facilitating the easy movement of charge carriers, which gives rise to current. So what we are doing here is biasing, and this biasing can be done in two different ways. One is forward bias and the other is reverse bias. So what happens in a forward bias? So in forward bias, what we do is the P side of the PN junction, this P side is connected to the positive of the external supply. This is the external supply, external voltage source. So this is P type or the P side of the PN junction. The P side we are connecting to the positive of the external supply, and the N side we are connecting to the negative of the external supply. So P to positive and N to negative, we call it as forward bias. So when we are doing this, what happens? The majority carriers of the P and N region will be moving towards the junction. So here this is positive. So this positive will repel all the holes and they will be pushed across the junction. Holes are the majority carriers. So the majority carriers will be pushed across the junction, and here this is negative, and this negative will try to repel these electrons and will try to push them across the junction. So what happens here is the majority carriers will start moving, will try to move across the junction, and because of this, what happens? This will reduce the width of the immobile charges. So the electrons that are coming here may combine with the positive charges on the N side, and the holes that are coming may combine with the negative ions here, and the width of the depletion layer decreases. So as we increase the external voltage, so more and more holes and electrons are pushed across the junction, and these immobile ions will get reduced, thereby reducing the width of the depletion layer. And at one point, the contact potential is, or the barrier potential is reduced to a very great extent. Now, when the PN junction is reverse biased, so what is reverse bias? In reverse bias, what we do is the P type of the PN junction, we are connecting it to the negative of the external supply. This is positive, this is negative. This is external supply, I say, or external voltage source. So how are we connecting in reverse bias? P type connected to the negative and N type connected to the positive. So this is what we call as reverse bias. So in reverse bias, what happens? Across the diode, when the reverse bias voltage is increased continuously, the depletion layer becomes more and more wider. Why the width? You can see here, the width of the depletion layer is increasing. Why it is happening here is because we have, this is negative, the holes will get attracted towards the negative terminal. So more and more holes are moving towards the terminal, means more and more negative ions are being created across on the P side of the junction. And the same way here, when N type is connected to the positive, all the negative ions are attracted towards this. So when the negative ions are moving away, more and more positive ions are being created. So there is creation of more and more positive and negative immobile ions. And because of this, the width of the depletion layer increases. So what happens here is there will be a small current due to the minority carriers, because the width of the depletion layer is more, so they cannot cross the junction. But what happens here is, because of the positive space charge region over here, so this positive space charge will attract the negative ions or the negative charges from the p side. Here negative charges are minority carriers. What are the minority carriers? I can say electrons are the minority carriers. So these minority carriers will get attracted towards the positive. And here, what are the minority carriers? Holes are the minority carriers. So these minority carriers will get attracted towards the negative space charge region. And because of this, there is minority carriers, there may be a small current flowing across the junction. Now, as we increase the reverse voltage, we have applied reverse bias and we are increasing the voltage. So, as we increase the voltage, what happens? These minority carriers, they get sufficient kinetic energy due to the strong electric field, because the depletion layer, the width of the depletion layer is increasing, the electric field is also becoming strong. And now these minority carriers, when they are getting sufficient energy due to the external supply, these free electrons, they will collide with the stationary ions of the depletion layer. We are having more and more stationary or immobile ions in the depletion layer. So the electrons that have become free, they have gained kinetic energy because of the electric field, strong electric field. They come and collide with the stationary ions. So when they collide, they knock out more free electrons in the depletion layer. So, and these free electrons that are knocked out, they will go and further hit the other ions and remove the electrons. So what happens here is more and more free electrons are produced because of these collisions. So this is a cumulative effect we can say. Due to this cumulative phenomenon, very soon huge number of electrons get created in the depletion layer and the entire diode will become conductive. So what was our aim in applying the bias? Either the forward or the reverse bias is to reduce the width of the depletion layer or to remove the depletion layer so that there will be movement of charge carriers across the junction, and because of this movement we have the current. Now because there are more and more free electrons that are there in the depletion region, so the depletion layer is breaking down and we'll have the diode to be conductive. And this type of breakdown of the layer is known as avalanche breakdown. Because the number of electrons produced are exponentially high, we call it as avalanche breakdown. But this breakdown is not quite sharp. This is one point we need to remember. All this we are discussing about a normal PN junction diode. So what happens when we have a PN junction diode? How is the movement or the diffusion current and the drift current we have seen, and the formation of depletion layer, and because of the depletion layer how electric field is generated, and the movement of holes and electrons is stopped because of the barrier, potential barrier that is formed. In order to remove this barrier, we are doing either the forward bias or the reverse bias. So in reverse bias, what we are seeing now is, as we increase the reverse voltage, because of the cumulative effect, more and more free electrons are generated in the depletion layer, and we have the breakdown of the depletion layer, because of which there will be a large current flowing, and we call it as avalanche breakdown. Now, what happens because of this avalanche breakdown? The electric current in the diode rapidly increases. More and more electrons, because of the flow electrons, you have the current. And this increase in current may permanently destroy the normal diode. So when the current increases, what happens? The diode may get burnt or it may get destroyed. But it means once you have used a PN junction diode in a circuit and you have applied a reverse bias voltage to make the current flow through it, because of the large current that is flowing, the diode, the PN junction diode may get destroyed and you cannot use it again. But to overcome this, what we are doing is we are going for a Zener diode. So what do we have in a Zener diode? We are trying to operate the Zener diode below the avalanche breakdown. Means even before the breakdown of the potential barrier happens and there is large amount of current flowing. No, we will try to operate it below that so that it can sustain the sudden spike of current. Means before the diode gets destroyed itself, there will be a breakdown and the diode will allow the current to flow. And this type of breakdown in the depletion layer, which is sharp compared to avalanche breakdown, we are calling it as Zener breakdown. So in a normal PN junction diode, if you see in a normal PN junction diode, we are calling it as avalanche breakdown. And because of the avalanche breakdown, what is happening? A large current flows through the diode, and because of which the diode gets destroyed. Now, by doping it suitably, we are trying to bring down that breakdown to a Zener breakdown. And this Zener breakdown is below the avalanche breakdown. Means if the Zener breakdown is happening at around 0.5 to 0.6 volt, this may be somewhere above 0.8 volt. So before avalanche happens, there is a Zener breakdown and the current flows through the junction and the diode is also safe. So Zener diode operates just like a normal diode. Diode here means the PN junction diode when it is forward biased. So we have seen completely the functioning of the forward bias. What happens here? The width of the depletion layer increases as we apply the forward voltage, and slowly the charge carriers will cross the junction. But when connected in reverse bias, a small leakage current flows through the diode due to minority carriers. This also we have seen. The leakage current is always due to the minority carriers. The minority carriers here are the electrons on the p side and holes on the n side. Now, in a Zener diode, what we are doing is we are doping it highly, high doping. So we take a PN junction diode and it is heavily doped so that the concentration of impurity ions will be high in the crystal. Means whenever you take a pure semiconductor and add a p-type impurity, that's a trivalent impurity, we are getting a p-type semiconductor, and we are adding an n-type impurity, we are getting a n-type semiconductor. But here, whatever the dopant atoms that are added, if you increase the concentration, the doping becomes high. More and more number of impurity atoms are added. So the higher concentration of impurity atom causes higher concentration of ions in the depletion layer. We have already seen the formation of immobile ions in the depletion layer. How a depletion layer is formed and what we have in the depletion layer, we have already discussed in a PN junction. Now, in Zener diode, what we observe is because of high doping, that is high concentration of impurity ions, there are more and more the concentration of the ions is also, the immobile ions is also more in the depletion layer for the same applied voltage. Whatever voltage we have applying before for a normal PN junction diode, even if we apply the same, but the number of immobile ions is more and the width of the depletion layer becomes thin. So we can understand the difference between the two. So when we compare the Zener diode with a PN junction diode, the doping concentration is high. And because the doping concentration is high, the number of immobile ions in the depletion layer is also high for the same applied reverse voltage. And because of this, what happens? The width of the depletion layer becomes thin. So when the width of the depletion layer is thin, the voltage gradient or the electric field strength across the depletion layer will be quite high. So because of the thin region, the electric field strength across the depletion layer is high. Now, as you increase the reverse voltage, after a certain applied voltage, the electrons from the covalent bonds within the depletion layer come out and make the depletion region conductive. So as we increase the reverse voltage, what happens? The electrons from the depletion layer, which are already forming the covalent bonds, they break and they come out. And because of these free electrons, the region starts conducting. So on increasing the reverse voltage, the current starts increasing because there are more and more free electrons. And a point is reached when the junction gets destroyed and a sharp increase in current is noted. So when the junction is destroyed, means the barrier potential is removed, there will be a sharp increase in current. So without much increase in the reverse potential, we may not increase the potential much, but the increase in current will be high, very exponentially high. And the current can be limited with the help of an external resistance. If we have to limit the current, now we may use some external resistance and limit the current that is flowing across the junction. Now we will clearly understand these two phenomena, the Zener breakdown and the Zener voltage. So when the applied reverse bias voltage reaches the Zener voltage, what we are doing, we have connected it in reverse bias and we are increasing the applied reverse voltage. So when the applied reverse voltage becomes equal to the Zener voltage, then what happens? The electric field in the depletion region will get strong and they will pull out the electrons from their valence band. So the electrons which are there in the valence band are pulled out because of the strong electric field, and these electrons, they gain sufficient energy from the electric field of the depletion region and they will break free from the parent atom. So they get separated from the parent atom, and at Zener breakdown, a small increase in voltage results in rapid increase in current. This is very important. There will be a sharp rise in current. Without much increase in voltage, the current increases rapidly. So this voltage at which the breakdown occurs, we call it as Zener voltage. Sometimes you may have to understand these definitions. Then the concept becomes very clear. What is a Zener voltage? The voltage at which the breakdown occurs, we are calling it as Zener voltage. Now, if the applied reverse voltage across the diode is more than the Zener voltage, the diode provides a conductive path to the current. So the excess current will flow through the diode and there is no chance for avalanche breakdown. So before reaching the avalanche breakdown or that particular voltage itself, the diode starts conducting. So theoretically what we say is Zener breakdown occurs at a lower voltage level than the avalanche breakdown. And the Zener breakdown is much sharper than avalanche breakdown. And the Zener voltage can be adjusted during manufacturing with the help of required doping. So we said it is heavily doped. So by varying the concentration of the doping atoms, we can vary or adjust the Zener voltage depending upon the requirement. We can do it at the time of manufacturing itself. We can set the Zener voltage. So when the Zener diode is connected across a voltage source and the source voltage is more than the Zener voltage, then what happens? The voltage across the Zener diode is fixed irrespective of the source voltage, because whenever the voltage is going high, the diode starts conducting and it will produce a path, and so across it remains constant. So the current through the diode can be of any value depending upon the load. So that is why we are always using a Zener diode to control the voltage. This we are also going to discuss in applications. How a Zener diode can be used as a voltage regulator, we will discuss in the applications also. So now when we see avalanche breakdown versus Zener breakdown, the Zener effect is dominant in voltages up to 5.6 volts. And the avalanche breakdown takes above that, means around 7 to 8 volts, the avalanche breakdown occurs. And they are both similar effects. In both the cases, the potential barrier is breaking down and there will be the movement of charge carriers. But in Zener effect, it is a quantum phenomena. Whereas the avalanche effect, it is just the movement of electrons from the valence band to the conduction band, like in any other electrical circuit. And avalanche effect allows larger current through the diode. So because of which the diode also may get destroyed. That is what we have seen. Now coming to the characteristics, voltage current characteristics of a Zener diode. So what are the voltage current characteristics? So for this, what we have to do is, we take voltage along the x-axis and we take current along the y-axis. So this is the voltage along x-axis, and we are taking the current and the forward current along the positive x-axis, and the reverse current we are taking along the negative x-axis. The same way, positive voltage along the positive x-axis, this is the positive x-axis, and the negative x-axis, this is the positive y and the negative y. So x-axis it is voltage and y-axis it is current. This is forward current and this is reverse current. This is forward voltage in forward bias and this is reverse voltage in reverse bias. So we will discuss both the forward characteristics and the reverse characteristics separately. So first, coming to the forward characteristics. So what are forward characteristics when we are connecting the Zener diode in forward bias? That is, P connected to the positive of the external supply and N connected to the negative of the external supply. We say it is in forward bias and we get the forward characteristics. What are the forward characteristics? We are going to plot the graph for the voltage, forward voltage along the x-axis and forward current along the y-axis. And how we get the curve is like this. As the voltage increases, the current also increases. And this is how it happens. And the function is similar to that of a normal PN junction diode. In a PN junction diode also we have the characteristic. Initially it is very low, but once the breakdown occurs, we call this as the knee voltage or the threshold voltage, there will be a rise in current. So this is the forward characteristic we see. It is similar to that of a PN junction diode. Now coming to the reverse characteristic. So when a reverse bias voltage is applied, how do we apply reverse bias voltage? By connecting the diode in reverse bias. Reverse bias means connecting P to the negative and N to the positive. A small reverse saturation current flows across the diode. This is, I told, this is due to the minority carriers or the thermally generated minority carriers. There will be a small current that is flowing. Now you see here in the figure, if you see the forward characteristic is there in the first quadrant. This is positive voltage and this is positive current. Now what we are doing, we are applying a negative voltage and we are seeing how the current increases. So this will be in the third quadrant. So as the reverse voltage is increased, at a certain value of reverse voltage, the reverse current increases drastically and sharply. This is very important. Now if you see here, there is a very small increase in current due to the minority carriers, but at a particular voltage, we will call it as Zener voltage or the Zener breakdown. We see here at the Zener breakdown, when the barrier breaks down, then there is a sharp rise in current. So this is an indication that the breakdown has occurred. And this voltage, we will call it as Zener voltage, which is denoted by Vz. Zener voltage is denoted by the voltage. This voltage is denoted by Vz. Okay, at which there is a breakdown and we are getting the Zener breakdown. Now, if you see here in this diagram, if it is a normal PN junction diode, what happens here is at a very high voltage when compared to the Zener voltage, there will be a breakdown. So this we call it as avalanche breakdown. Here we can compare both. We call it as knee voltage or the reverse voltage at which the breakdown occurs. We'll have avalanche. But the problem with the avalanche breakdown is the diode itself gets spoiled, means we cannot use it again. So it is always advisable to dope it in a suitable manner so that the breakdown occurs at a very low voltage and the diode starts conducting. Now we are going to see the applications of Zener diode. Where all we are going to use this Zener diode. First one is in voltage regulation. How do we use it to regulate the voltage? So regulating the voltage of a current is its ability to keep the output voltage fixed. Whatever may be the input, the output has to be fixed. So how we are going to use this Zener diode as a voltage regulator? So this is a circuit. No? What we have here is a Zener diode. This is a symbol. Whenever we are using or representing it in a circuit, we use this symbol for the Zener diode. Okay. The circuit is connected across an input voltage. So we have the source here. So this is connected in reverse bias. No? So this is positive. So positive will be connected to the negative. Like this you will have the supply. So this is the input voltage source connected across the Zener diode. This is the RS and this is RL, the load. So let us see how it functions. So RS is the current limiting resistor. So whenever there is a current that is flowing, I said we can limit it with the help of the resistance. Resistance is what obstructs the flow of current. By selecting a suitable resistance, we can limit the current flowing through the circuit. And Vs here is the voltage source. The source that we are using, we are calling it as Vs. And RL here represents the load resistance. This is the load across which we get the output. Now RS absorbs the voltage fluctuations. This is limiting the current, we said, no? It will absorb the fluctuations so as to give a constant output voltage. Now, until the load voltage is less than the breakdown voltage, the Zener diode does not show any conduction. Means there is a breakdown and the barrier has not still broken down. You are keeping on increasing the voltage, means the external supply is increased. So the diode is not conducting till there is a breakdown. So there you will have the current. But what happens once the voltage is high? So as the voltage at the load increases than the breakdown voltage, then what happens? The device starts conduction in the breakdown. So this will start conducting. Okay. So at this point, what happens at the breakdown region? The voltage across the load remains constant. Whatever is excess, so that flows across the diode and you will have a constant output across the load. Next one is in switching operations. We also use a Zener diode in switching operation. Why? Because there is an abrupt transition from low to high. So initially it is very low, but once there is a Zener breakdown, there is a sharp rise in current. The current increases rapidly without much increase in the voltage. So because of this, the switching characteristics we also use, it has lot of applications in computers. And the next one is meter protection. So wherever we are using meters, no, it may be a current meter, an ammeter or a voltmeter or any type of measuring instrument, a Zener diode can protect a meter from excessive voltage applied to it. So what we do here is a parallel connection with the Zener. You have a meter which is to be protected and this is the meter to which we are supplying the input. The input is given. And when we connect a Zener diode across this, what happens whenever there is excess current that is flowing or the voltage is excess, this will start conducting and the output remains the same. Across this or the load you take the output. So a parallel connection of Zener with the meter. So we are doing a parallel connection of the Zener diode with the meter, whatever meter we are taking. Excess current will pass through the Zener rather than the meter. So thereby protecting it from severe damage. And it is also used in clipping circuits. So what is a clipping circuit here is, in clipping circuit, the peak of the applied input is clipped off. Whenever there is a peak and it has to be limited, we use a Zener. So it can be used for clipping. Clipping is done to protect the voltage sensitive devices from over voltages. Whenever the voltage is going high and that may damage the instrument, so we use clipping circuit so that the voltage has to be kept constant or within the limits. So for that also we use Zener voltage. So that's all in Zener diode. For understanding of this topic, you can refer to the books Semiconductor Physics and Devices by Donald Nieman, or you can also refer to Semiconductor Devices Physics and Technology by Simon Z and Ming-Quinn Lee. Thank you and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.